on from the handout I gave you, the worksheet, the handout I gave you, page 4, I think it's on.
Yeah.
Let's write a mechanism. So we are focusing on SN2. Of course, how do I know this is SN2? Is there a hint here that would tell me that this is SN2?
One step.
But that doesn't define SN1 or SN2. SN1 can also have a bad leaving group.
It's primary.
It's a primary. Remember, look at substrate first. That's your first thing. Then if that's the same, then you look at nucleophile. If those are the same, then you look at blah, blah, blah. Yes, so this is SN2 because that's a primary substrate. Primaries do SN2. Tertiaries don't do SN2, right? And you're absolutely right that it's a bad leaving group. You have to remember that OH is a bad leaving group. So when you write the mechanism, yes, it is SN2, but you first have to make that a good leaving group. Only then can substitution happen. Isn't that right?
Yep.
Did you guys already write this mechanism?
Yep, I did.
Okay, good. So what should be the first thing that happens?
The propanol reacts with the HCN to make OH.
So that doesn't break on its own. I thought I heard somebody say so that doesn't break on its own, but it can react with the alcohol.
Yes.
What kind of reaction would that be? Louder?
Addition? Not
Not
addition.
really.
Not addition.
Acid base.
Acid base reaction.
This is electron rich. It can act as a base. Can that donate a proton?
Yep.
Absolutely, it acts as an acid. The base takes the proton and creates what? So the point here that I'm trying to make everybody understand, the reactions are driven by electrons. HCN bond doesn't break on its own. There's no reason for that bond to break on its own. It's breaking only because there's something else coming and grabbing the proton. It might be a polar bond, but it's not going to break. So what is that going to create? It's going to?
A conjugate base and a conjugate acid.
Agreed? Yeah. Now, this is a very good leaving group. Why is this a very good leaving group?
Because it's cycling.
Louder, please.
Because oxygen spacing is octet.
Okay, so?
The bonds are unstable.
Why? We're just going in circles right now.
Like a poor base.
Exactly. What does it become when it's left?
Water.
When the leaving group leaves, what does this become?
H2O.
It becomes H2O. Is H2O a strong base or a weak base?
Strong base.
Ooh,
Weak
never.
base. Weak base.
So a weak base is a
Good leaving
good
group.
leaving group.
Weak base.
That's a
is
good leaving group because after
weak
it's left,
base.
it's a weak base. A weak base is a good leaving group. Okay, cool. So now we are ready for substitution. Isn't that right?
Yeah.
So this is step number 1, which is not SN2. It's just making a bad leaving group into a good leaving group. But once we get a good leaving group, we can now do SN2. So when we are doing SN2, what's the nucleophile in this example?
The cyanide ion.
Okay. And if it's SN2, which direction does the nucleophile come from?
Opposite the
You
leaving group.
Must
180
show it
degrees.
that way. I just glanced at some of the quizzes, not grading, just glancing through. I'm not seeing that. It cannot be at an angle. The transition state when you're drawing, and I don't care how the book shows, guys, we are learning something here, so let's do it correctly. The leaving group and the nucleophile have to be opposite, which means this is not opposite. Is this opposite?
No.
They have to be at what angle to each relative? to
180.
each one?
180 degrees.
Exactly. So let's draw it that way, that they are actually 180 degrees from each other. Okay, what am I missing here?
Partial charges.
Which would be what and where?
Partial pop.
Very good.
OH2 and then partial negative on CN.
Do you all agree?
Yep.
Great. And then, of course, it goes through the transition state. What is the product? Agreed? Now, why did I draw it this way? Well, does it matter? Because is that a stereo center?
No.
No, it's not a stereo center. So I drew it this way. You could have drawn it this way. Maybe somebody drew it this. That will probably be weird. The point is, it doesn't matter because that's not a stereo center. But the nucleophile has to come from the opposite side of the leaving group for SN2. Do we all agree?
Yep.
Is that okay? This one? Okay. Let's look at the next one. I think that's also from the handout, same page. You first have to give a product and then we'll write a mechanism. Any guesses what the product would be? Hey, Mom.
Oh, yes.
Thank you so much. Anybody for what the product will be? Louder? Okay, so when you're looking at this guy, that's the molecule, isn't it?
Yep, that's the H2O.
So what part of it do you think will become part of the product?
The OH.
So the product, final product,
will be
and what else?
H.
That's the overall equation. Now let's write the mechanism. So do we have a good leaving group?
Yes.
Okay, so we have a good leaving group, so we don't need to worry about it. What's the nucleophile?
The hydroxide.
No, there's no hydroxide in water. It's
Oh.
not ionic, it's a covalent compound.
Oh.
Polar, but covalent. So what's the nucleophile? It's the whole molecule. It's not cation, anion, right? It's not ionic. But it's SN2 because that's primary, so it's SN2. Nucleophile comes from the side opposite to the leaving group. Agreed? Let's draw the transition state. So the transition state, once again, keep it at 180 degrees, guys. And do not forget the charges. So what will be the charges and where? Anybody?
Partial negative to BR and then partial positive to HO2.
Very good. Absolutely. Everybody okay? And then this goes through. So what does it give us when it's gone through? Do you agree? But that's not the product. That's not the final product. So this is our SN2 step because substitution actually happened. But we can't stop there. The product will not be ionic. The product has to somehow come to a neutral state. So if you look at this guy, what can this guy do to get rid of the positive charge? Give a proton, which means react as what? Exactly. So what will this react as? Acid or base?
Acid.
Because it wants to get rid of one H and plus. Exactly, H plus. Who's going to take the proton?
The bromine. The bromide.
So, a base, right?
Yep.
Now, in this example, we have two substances that could potentially act as a base. One of them is bromide, Br minus. Is there another substance that could also act as a base and take a proton?
Water.
Which is a stronger base, Br minus or H2O? Don't be so quick. Please don't be so quick. What is the only way, the best way to decide which of these is the stronger base?
Weak conjugate
Look at
acid.
their conjugate acids. What's the conjugate acid of Br minus?
HBr.
And what is the conjugate acid of H2O?
H3O plus.
Which of these is the stronger acid?
HBr.
So if this is the stronger acid, which of these is the stronger base? So please don't be in a rush there. It's not about negative only, it's looking at the whole thing. The weaker acid comes from the stronger base. The weaker conjugate acid came from the stronger base. So no, it's not Br minus that takes the proton. Of course, it's floating around. It's all in solution. So all of these things are floating around. But it is actually H2O that's stronger base that takes a proton and gives us the final product. Oh, I'm missing the final. Final product and hydronium in this case. But what is H3O plus and Br minus together? What is that equal to?
H2O and HBr.
There you go. H2O and HBr. So please remember, strong acids when they are dissolved don't stay in their own shape. They like you know already, HCl in water is hydronium plus Cl minus because of those. So we are not getting HBr per se, we are getting equivalent of HBr by those two entities. But does everybody understand? So what about the last one? Now that's not in the handout. So once again, assuming SN2, because what kind of substrate would this be?
Secondary substrate.
But is that a good leave? Yes, Vincent.
Sorry.
No, go ahead.
Real quick, for
Yes.
the transition state on that problem,
This one?
how was special bond?
Because it gave electron density. Isn't that right? It's giving electron density. And what's the charge on this oxygen? Anybody? 0.
0.
What's the charge on that oxygen?
Plus
So
1.
what's between 0 and plus 1?
Partial plus.
Remember, transition state is the middle point between the reactant and the product for that step. Do you see that? And another way to reason that out is that, hey, it was neutral, 0 charge, but it's giving electrons, so it's going to become positive somewhat. Does that answer your question? Okay, this is, you haven't seen this kind before, but it's very similar to what we are doing here. That's a secondary substrate. Secondaries can do SN2 and SN1, although we are right now only thinking about SN2. So let's just focus on SN2. Is this a good leaving group or bad leaving group? What do you think?
Bad leaving group?
And why is this a bad leaving group?
Because it's not a halide? No.
What's a good leaving group? Louder. So what's a bad leaving group? There you go.
A good base. So it's a strong base.
A good leaving group is a weak base. That though, if that leaves, when that leaves, what will it become?
OETO minus ethyl.
If this leaves, I'm not doing stereochem just now. If this leaves and kicks out, nucleophile comes in, what does it become? Is that a good base? Pretty good. How do I know it's a good base? Because, well, yeah, but there's nothing to compare it to right now, right? So how do I know it's a good base in absolute sense? There's no difference between the two. Guys, please understand and recognize what is the structure of water? Anybody?
HOH with 2 lone pairs on the O.
HO bent Vespa, right? If I replace one of those H's with R's, what does it become? An alcohol. Isn't that right? So what is the conjugate base of water?
Hydroxide.
Isn't that right? If it loses a proton?
Yep.
Isn't that right? So what's the conjugate base of an alcohol? If it loses an H plus, what is the conjugate base? Same thing. There is no difference between their acidities, basicities, reactivities, water and alcohols. They're very, very, very similar to each other. We all see that. So when I'm seeing this guy, without knowing too much about it, it's going to be very similar to this guy. And hydroxide you've seen before.
Yep.
Isn't that right?
Yep.
In the first example, do you remember we said alcohol is a bad leaving group? Why is it a bad leaving group? I forget what I had there, but alcohol is a bad leaving group because when it leaves, it becomes this. Isn't that right? Did we call this a bad leaving group?
Yep, it's a strong base.
So then that is a bad leaving group as well. All we did was instead of the H, instead of this H, we put an ET, same thing, no difference at all. The structure is the same, the electronic characteristics are the same. their reactivities, behaviors are very, very similar to each other.
So to have it in words,
Yes.
a bad living group is because of?
Because it's a very good base.
Oh,
It's as good a base as hydroxide.
that's
And
why it's bad.
hydroxide, we call it a good base, so then we should call that a good base as well. Do you see that? Yes,
Yeah.
no, maybe.
Yep.
Mark, I'm seeing a question on your face.
Yeah, I'm just processing, I'm
Right.
processing,
So
I'm
my
slow.
point, the point I'm trying to make here is, when you think of alcohols, think water. Because alcohols and water are very similar to each other. So whatever water tends to do, alcohols will also tend to do that, because the structures are very similar. Everybody okay? Yes? Okay, so coming back there though, it's a bad leaving group. Okay? So before we do substitution, what do we have to do?
Make it
We
a
have
good,
to do an acid-base reaction, make it into a good leaving group. Exactly. Where is the base? Or what is the base? Base.
HBr.
Who's going to take a proton?
Oh, the substrate.
yeah,
The
Who's going to give a proton?
the acid.
the
Which is what?
HBr.
So the base takes a proton from the acid, right? It's exactly the same as the first one we wrote, by the way. Exactly the same. The fact that now instead of H we have ET makes no difference at all. So nothing else. By the way, should I change that stereo center?
Yes.
Are you sure?
No.
Not yet.
Should I change it now? I mean, for this step,
Oh.
that
No.
stereo center.
No,
No, why
Not for
not?
this step.
you're not SN2.
The reaction didn't happen here. The reaction happened at the oxygen. So should we change that? No, not at all. This is still the same. Isn't that right? Now we have a good leaving group. Please notice the similarity between that leaving group and, without showing anything else, and this leaving group. There is no difference between them because alcohols and water behave very, very similar to each other because they have similar structures. Everybody okay? Now we have a good leaving group. So a nucleophile will come in. What is the nucleophile? What's the nucleophile?
The Br minus.
And SN2, so it's going to come from the opposite side of the leaving group. So the transition state. Do you guys agree? Charges, what, where?
The partial negative on the bromine and then the partial positive on the leaving group.
And once the leaving group has left and the nucleophile has come in, should this stereochem change?
No,
Yeah. No, not there.
And should that one
Yes.
change?
Yeah.
What does it now become?
front.
And plus, what's the byproduct, which we don't really care about, but what is it?
Ethanol.
Do you guys see that? So, nucleophilic substitution is, the substrate can have any leaving group as long as it's a good leaving group. In the quiz, okay, maybe we should talk about the quiz just yet, sorry. Any questions about SN2, guys? There was a question, I don't know if my email made any sense, Eric.
Yeah, I
That's-
think I'm thinking about it wrong.
No, you're not. Actually, you're thinking, and I had that conversation with a couple of students also today. You guys are thinking absolutely right. So the question was, just as an example, I'm just going to say R. I reacts with Br minus becomes RBr plus I minus, right? So the question was, well, we said nucleophilicity. If you look at how do you decide what's a good nucleophile or better nucleophile, nucleophilicity increases in that direction and it increases in this direction. And isn't that right?
Yeah,
So, well, in this case, isn't that a better nucleophile than this?
Yeah.
Absolutely, it is
Yeah.
actually tiny bit better, although we can do this reaction very well. So the question was then, why can't this just go attack this again and go back? The answer is yes, absolutely. That's a good part. Yes, it will. But then when you have reversible reactions, they reach a point of equilibrium, right?
yeah.
And this you've done in Gen Chem. What's that rule that decides which direction the equilibrium lies in? There's a rule.
Le Chatelier's
Le
principle.
Chatelier's principle. Exactly. So that comes into play. So depending on what I need in the lab, let's say I'm doing this reaction and I need this more. Well, then I can run a reaction in such a way that Le Chatelier's principle supports that side. What are some things I could do based on Le Chatelier's principle that would support the product side relative to reactant side?
Add more reactants.
Okay, you can, but both of them, or maybe take one of them in excess, and push it in that direction. What else could I do? If not add more reactant, what else could I do? Maybe take away the product. As you're doing a reaction, there are multiple ways of designing these experiments. I could maybe, as I'm doing a reaction, I'm also taking this out of the system so that Le Chatelier's principle takes it more in that direction. So that's a great question. And then most of these reactions, by the way, that I'm talking about can go in either direction. What decides which direction depends upon a multiple factors such as substrate, nucleophile, leaving group, solvent, and Le Chatelier's principle. They all come into it.
Okay, can
Please.
so I get that,
Yes.
but what I'm not getting
Okay.
is that, so you have a leaving group.
Yes.
We evaluate the quality, as in how easily it leaves, by the inverse of the basicity.
Right.
Right. And there's no special rule about as you get bigger, you know, because there's kind of a special rule for nucleophiles. As it goes down, basicity goes down, but it goes up.
So there's a rule for basicity as well.
Okay.
What happens, we talked about this last quarter. So please, let's go back to last quarter. Does anybody remember, in terms of base strength, if you're looking across the period, does the basicity increase or decrease? C minus, N minus, O minus, F minus, it become stronger base or weaker base?
Weaker base.
Oh shoot, I did do that wrong. Vincent, you and I were discussing that earlier today.
Basicity increases.
No, I wrote that wrong. They are right. No, I wrote that wrong. Please fix that. Please fix that. Yes, C minus is a stronger base compared to N minus, compared to O minus, compared to F minus, because electronegativity is increasing. So O minus is happier than N minus would be, because O is more electronegative, more loves electron density more. Let me rewrite it again and fix it, please. Let's fix it. So, if this is the periodic table, basicity increases actually this way. Please fix that. Basicity decreases this way.
Huh?
Basicity. We're talking about base strength. O minus is a stronger base than S minus would be. F minus, technically speaking, is a stronger base than Cl minus would be, so on and so forth. Everybody okay? Nucleophilicity, though,
Be a stronger base.
going across the period should follow the basicity, but going down the group goes in the opposite direction.
Okay, I get that. What I'm not getting is the
So-
leaving group issue.
Exactly. So now the leaving group. Technically speaking, weaker nucleophile, technically speaking, is a better leaving group, because we don't want it to come back and go in the other direction, right? Technically speaking. So in this case, if you're comparing across a period, leaving group will follow that. But if you're comparing down the group, let me make sure I'm getting that thing correct in my head. It's following the basicity pattern. So the stronger, it's actually going to go this way. You're absolutely right.
Wait,
So I minus
um,
is a very interesting thing. It is a great nucleophile, actually a wonderful nucleophile. But on the other hand, it is also a great leaving group. Absolutely.
Can you give any intuition on this?
Intuition?
Yes.
So, tell me, what do you mean by intuition?
Well, okay, so I feel like if it releases easy, it shouldn't
But that's
stay.
where, no, you're absolutely right. So how do we make it work for our favor? That's when our experimental design comes into the place. And I use Le Chartier's principle. Because, hey, this is what I want, primarily speaking. I don't want it to go back because it can actually do both. So to favor this, I'm going to choose my reaction design in such a way that it favors that side of the equilibrium compared to this side of the equilibrium. That's when I will design an experiment where maybe I'm taking one of these in excess. So because these are in excess, it pushes. Or the best way actually would be to do a reaction setup in such a way that as it's happening, I'm taking this out of the system. So it keeps pushing and pushing and pushing and pushing to. So that's where our experimental design comes into play. But the question is great, you're absolutely right. There are lots of things, such as even Br for that matter. Of course, not as much as iodide, but bromide is also a great leaving group and also a really good nucleophile. So then you've got to figure out how are you going to do this in order to get what you want. Primarily. That's what I meant to say. No, that's absolutely right. So that's why it was actually a great question. Guys, please make a note of this if this helps us in terms of comparing basicity to nucleophilicity to leaving group ability as well.
Leaving groups
Yes.
go up as you go right.
Yes, exactly. They become a better leaving group.
I heard
Okay.
you said that leaving group going down follows basicity.
Opposite.
Opposite
Strong
basis.
base
Oh.
is a bad leaving group, weak base
Okay.
is a good leaving group. So
Okay.
basicity and leaving group are opposite each other. Basicity and leaving group are opposite.
Oh, okay. Inversely.
Yeah. So hopefully this makes sense. I think I told you wrong earlier in the morning, Vincent. Please correct it. Please correct it. Any other questions? Okay, then let's, oh yes, come on.
Can you explain a little bit why we're taking out RBRs to balance out the equilibrium equation?
Say that again?
Why we're taking out RBRs to balance out the equilibrium?
No, I wasn't, oh, product.
Product.
Because if you take out the product, the equilibrium is going to establish itself again.
Yes, wouldn't it make more RBR?
Exactly.
That's the point.
Exactly, that was the point. If I wanted more of RBR, the product, whatever else is, I forget what I wrote earlier, iodide, I think that's what I wrote, right? Here's
Yeah.
your equilibrium, what did I have here?
Ri plus Br minus.
Okay, cool. So if I want this,
Okay.
so if you keep removing it, it makes more.
I thought you were saying that you wanted the iodine.
No,
Okay.
but yeah, if you wanted this, not that, then you got to do the opposite.
Okay.
Absolutely. Everybody okay? Cool. Let's talk about SN2 because we have, I think, excuse me, we finished SN2. Let's start SN1. Personally speaking, I love SN1 because I find it way more funner than SN2. SN2 is kind of boring in the sense it's one step, no intermediate. Right? SN1 is kind of fun. Okay, let's start SN1. So,
Awesome.
SN1 stands for substitution nucleophilic. What is one?
You
Uni
Uni
molecule?
molecular. Yes. What does that mean?
Only the substrate affects the rate.
Exactly. The rate of SN1 reaction depends only on the concentration of the substrate. The nucleophile is not part of the rate equation. The nucleophile does not affect SN1 at all. We'll talk about why. Why is that? Why does the nucleophile care? We'll talk about that. But it's called unimolecular because only the substrate affects the speed with which SN1 reaction would happen. Okay, let's take an example. We'll write the mechanism and discuss the details as we go along. So any guesses what the product would be? Again, what is that?
Ethanol.
Ethanol. It's an alcohol. And what did we say about alcohols?
Bad leaving group.
Okay, fine. What else did we say about alcohols? Alcohol is not a bad leaving group. Alkoxide, OR, is a bad leaving group.
It's the same as
It's the same as what? Alcohols are same as what?
Water.
Water. If that's an alcohol, this is water. Isn't that right?
Yep.
Everything else is the same. Okay. So what part of water becomes the product? What part of water molecule becomes part of the product?
The OH.
Isn't that right? So what part of alcohol should become part of the product?
RO.
That part. So what's the product? The product is where OR, which is OET, becomes part of the product. What's the byproduct? Anybody?
HBr.
HBr is the byproduct. Okay. Now this is, what kind of substrate is this? Primary, secondary, tertiary?
Tertiary
Can it
substrate.
do SN2?
No.
It does SN1, right? Now SN1 is not a concerted mechanism. It's a step by step mechanism. So let's look at the mechanism SN1. Step number 1 is where the leaving group leaves. Can someone tell me what would that create?
The carbon cation with a
The
plus,
carbocation.
like how do you call it?
And
Negative. Yeah.
this is the formation of the carbocation is the rate determining step. This is the step that decides how fast or slow the reaction would be. Step number 2, once we have created a carbocation intermediate, the nucleophile comes in and attacks. Which part of ethanol is the nucleophilic part?
The ETO. The ethyl.
Where in ethanol is the highest electron
OH.
density? Oxygen. Due to polarity, because of the shape, the polarity, that is the delta minus end, right? So the nucleophilic center attacks the electrophilic center. What does that create? Do you agree? But can that be the product? If it has a charge, can it be the final product?
No.
Nope.
No. Louder?
Because it has to be neutral.
Exactly. So what does it need to do in order to become neutral?
Water.
What does it need to do to become neutral?
Donate the proton.
It needs to get rid of a proton. If it got rid of H plus, it will become neutral. Isn't that right?
Yep.
So what does, in other words, if it wants to get rid of a proton, what does it need to react as?
An
An
acid.
acid. What does an acid react with?
A base.
Base. In this system, what could be a base? Again, look at your choices.
Br.
ETOH.
So there is Br minus or there is ETOH. Which is the stronger base?
Let's do the
Don't be misled by the charge. You've got to look at their conjugate acids. Which is the weaker acid of the two? Of course, always keep your pKa tables with you. I gave you guys pKa tables last quarter. If you lost it, it's there on canvas, printed out. Keep it with you so you can compare their pKa values and then decide. Yes, Carrie?
Is the ETOH
OH2 the same as H3O?
Exactly, exactly. If you look at the structure of H3O plus, what is the structure of H3O plus? Isn't that right?
Yep.
What is ETOH plus, OH2 plus? Same, except one of the H's is replaced by ET.
Right, enough.
Everything else is the same. So the answer to your question is yes. Because those two are the same, these two are also kind of the same. The pKa values are very, very close to each other. Absolutely. I forget the pKa values, but that's a great point, Carrie, that if we consider this to be a weaker base than HBr, then this is also very likely going to be a weak, did I say weaker base? I think I did.
Stronger base.
Let me start again. If we think hydronium is a weaker acid compared to HBr, then it's very reasonable to say that this is a weaker acid compared to HBr. Absolutely. So if this is weaker acid, which is the stronger base?
ETO.
ETOH2
Absolutely.
plus.
No, that's the weaker acid.
Oh.
So this is the stronger base.
Okay, ETOH, ethanol.
Right? So please don't be misled by the charge. Charge does not always translate into stronger basicity. You have to really pause, you got to assess and then decide. So what is this doing? It's taking a proton and creating the final product. The point is, we showed 3 steps here. But which 2 steps in this 3-step mechanism is the actual SN1 process?
First two.
Exactly. These are the 2 steps in this mechanism which are actually doing the substitution reaction. The third one was not really a substitution process. It was an acid-base reaction to get the neutral product. Substitution happened in combinations of 1 and 2. Does everybody see that?
Yep.
So SN1 reaction, SN1 mechanism goes through 2 steps. The first step is to make the carbocation. This is the rate determining step. The second step is where the nucleophile attacks the carbocation and gives us whatever it gives us based on what you're using. Everybody with me?
Yep.
Yes.
If you had like a secondary, would you do SN1 or SN2?
Good questions, just not there yet.
Oh.
Yeah, exactly. And but we're getting there slowly getting closer. We're not there yet. But do we understand this mechanism? We'll write it a few times, different forms of it, but if there are any questions, please tell me. Now, yes, Carrie, yes.
I have a question on like the degrees, like primary, secondary.
We haven't gotten there yet.
Okay.
Give me a couple more minutes. That's my next thing that's where we are headed next. But before we do go there, I just want to ask one thing. This is Gen Chem coming back, guys. When you talked about thermokinetics and all of that stuff in Gen Chem, if you know this is the rate determining step, which substances in this reaction will affect the rate of this reaction? Knowing that step 1 is the rate determining step, which substances will affect the rate of this reaction?
The carbocation intermediate?
That's not a reactant, that is an intermediate. Intermediates never affect.
Is it just the substrate?
Why just the substrate? Why not the
Oh, because
nucleophile?
it's, yeah.
Because that's what the rate.
Because nucleophile comes after the rate determining step. Hopefully you guys learned this in Gen Chem when you did kinetics, or maybe at least hopefully you remember. The steps in a mechanism before and till the rate determining step, or through rather, I should say rate determining step, affect the rate of the reaction. Steps that come after the rate determining step do not have any effect on the rate of the reaction. So any reactant that comes into the picture either before or through the rate determining step will come into the rate equation. But any reactant that comes after the rate determining step does not come into the rate equation because it doesn't affect the speed of the reaction. Yes?
But does the solvent that you choose affect the rate?
That's a good question as well. Can you hold on to that part? It will, absolutely, because like we were discussing this morning, you're creating ions. So anything that stabilizes the ions makes this go faster, and therefore the whole thing will go faster. But we're not there yet again. The point I want to make is, and that's what I'm emphasizing on, the reason why only the substrate affects the rate of SN1 reaction is because that's the only reactant that has appeared in the rate determining step or before the rate determining step. The nucleophile does not, because it comes after. Is everybody following this? Can I say it one more time? Reactants that appear in the mechanism before the rate determining step or in the rate determining step affect the rate of the reaction. Reactants that come in the mechanism after the rate determining step do not affect the rate of the reaction. So that's why in this particular case, the nucleophile is not part of the rate equation because it comes after the rate determining step. Yes, Mark?
Oh, no, I
Oh, I
was,
thought your hand was.
well, I was just thinking about the video, that it goes like this,
Yes.
and then it gets there.
Yes.
And then
So-
it goes fast.
So this is your rate determining step, which means it has the highest activation energy. Once you get the carbocation, then, right? Now in this case, we have a third step. 3 steps. This is our step number 1. Bless you. Step number 2, step number 3.
And where is the rate?
Which has the highest activation energy?
Number one.
Exactly. So that is a rate determining step. So what do we have here? We have reactants here, we have products here, right? Who exists right here?
The intermediate.
Carbocation. Who exists in this example? In this example, who exists there? You have this protonated thing that exists there. And then of course that goes to the products. So yes, absolutely, the activation energy of step number 1 is the highest because it's the rate determining step. But the nucleophile doesn't come in till after. So who cares what the nucleophile is? Or how strong or weak the nucleophile is? You guys with me?
Yep.
That is the reason why. That is the reason why, generally speaking, there are exceptions, generally speaking, we use a weak nucleophile for SN1. Because it doesn't matter, then why use a strong one, which could potentially create other issues which we'll study about in a week or so. So if SN1 is the goal for a tertiary substrate, then a weak nucleophile is better. This takes me to a term which I kinda mentioned yesterday, solvolysis. Does anybody remember the term solvolysis? What is solvolysis?
That's where the solvent is the nucleophile, right?
Solvolysis is a substitution reaction. It can also be SN2, of course. If it were primary substrate, then it has to be SN2. But the point is, it is a substitution reaction where the nucleophile, the solvent is also the nucleophile. So what are the common solvents that we could encounter behaving as a nucleophile in a solvolysis reaction? Well, this is one example right here. I could do this example, this reaction using this guy as a solvent. It will serve 2 roles. It will dissolve everything and also act as a nucleophile, giving me the product. It's really a solvolysis reaction. Yes?
Sorry, can you read out what it says?
Oh.
So,
Is equal to nucleophile.
oh, I was talking about the first part. So,
Substance.
substitution.
Substitution. Let me write there. I didn't have enough space there. Solvolysis is when it's a substitution reaction. Didn't want to write the whole big word. In which the solvent is also the nucleophile. And the common solvents that you will come across in solvolysis reactions such as this: water, alcohols, ethanol, methanol, isopropanol, whatever, different kinds of alcohols, or even carboxylic acid sometimes. So these substances are doing two things in those reactions. They're dissolving everything, solvent, but also acting as a nucleophile to give us the substitution product. You guys with me? Yes? By the way, when the solvent or is the nucleophile or the and the solvent, we call it hydrolysis. Makes sense, right?
Yep.
Solvolysis. Any guesses? What if it's alcohol?
Alcoholysis.
Exactly. Not alcoholism. That's totally different. This one I forgot. What is it?
Carboxyl.
Carboxylic
I
acid.
don't think it has a name. If ammonia were the solvent and the nucleophile, because it can at low temperatures, that's a liquid, then it's called aminolysis, and so on and so forth. Don't be confused with all of these terms. The point is, they're all solvolysis reactions where the solvent is also the nucleophile. Everybody okay? Now, as I said, this is one example of a solvolysis reaction. By the way, have you guys, as I'm erasing, because I don't like silences, have you guys heard of the term solvation?
Salvation.
Salvation.
Not salvation.
Army salvation.
This is chemistry, not spiritual healing. So, now you made me forget it. Solvation. Okay, have you heard of hydration?
Yeah.
Solvation, hydration. So what is that? What happens when there is hydration happening?
Drinking
Water is
Okay.
added.
Okay, that was too general a question. Let me make my
Wait.
question a little bit more directed. Why does salt dissolve in water? Why does sugar dissolve in water?
It's ionic.
Okay, why does sugar dissolve in water? It's not ionic. Why does salt dissolve in water? You say it's ionic. Okay, so what? Louder? Okay, so what? Go deeper. Why does salt dissolve in water? So salt is what?
NaCl.
It dissolves in water, right? What happens when salt dissolves in water? What happens to these guys?
It dissociates into its ion.
Why does it dissociate into its ions?
They're divorced.
Louder?
I was making a joke.
What was the joke?
Divorce.
I said they're divorced.
They divorced. Okay, who came in between them
Another woman.
to separate them?
Another woman.
What is
Water.
that? What is that other person? Woman, man, whatever.
Water.
But who's that other person in this example?
Water?
Right? What is water doing? What water is doing is, and you've done this in Gen Chem, I know for a fact, what water is doing is the negative end of the water is surrounding the positive ion. Isn't that right? Lots and lots and lots of layers. That's solvation. That's hydration. The interaction that the water molecules are having with the ions, and of course the positive end surrounds the chlorine and so on and so forth, that's what's causing them to move away, isn't that right? Same thing happens with sugar. Sugar is a highly polar molecule, so depending on the polarity, the positive ends of the solvent surround the negative end of the molecule and vice versa. That is solvation. Solvation, is that a physical process or a chemical process?
Physical.
Exactly. There's no chemical interaction here. Those are IMFs, intermolecular forces. This is a physical process which is causing the or rather allowing the solute to dissolve in the solvent. Isn't that right? Everybody? Not to be confused with solvolysis. Solvolysis is a chemical process. It's a substitution reaction, chemical, where the solvent is the same as nucleophile. So please don't confuse the two. Solvation is just helping solute dissolve in the solvent. That's called solvation. Solvolysis is a chemical reaction. Are you guys okay? Okay.
Yeah.
Oh,
Not good.
let's do one more. Oh, I asked you a question yesterday in the lab, and I said, think about it and tell me. You thought I forgot. I am getting old, but not that old.
Both of us, all of us
Let's
forgot.
do that. You almost.
Wait, you asked the question.
Yeah, I did.
You sure?
Yes,
Yes, you did.
I don't
do
know.
that. Good try. Just not there. Okay. Something similar to the question I asked you yesterday. We'll get to that question also. But something similar to that. Okay, so let's say we have this alcohol. What kind of alcohol is it? Is it primary, secondary, tertiary?
Primary.
You guys agree?
Yep.
Yes.
But it's also, what else is it?
A bad, no.
It's
Oh.
next to a. So
A
what do we
lilac.
call that?
A lilac.
It's
A lilac.
lilac primary. Exactly. It's a lilac. It's primary, but also a lilac. Do you guys agree?
Yes.
Yep.
Okay, so let's say this reacts with, can you tell me what would the product be? Just the product. We'll write the mechanism after. What would be the product?
CL will replace,
Say again?
CL will replace the OH.
Okay. Cl will replace the OH, a substitution reaction, and?
H2O.
Okay. Do you all agree?
Yes.
Let's write a mechanism, SN1. Can it do SN2? Actually, yes, it can do SN2 as well. It can do both. Why? We'll get to that part later. The comparison of the two, we'll get to that part later. But you probably saw it in lab. Crotyl chloride was pretty good for both reactions, right? It reacted very fast for SN2, it reacted very fast for SN1 as well. Because it's primary, but also a lilac. Okay, cool. Let's write a mechanism this time for SN1. So what do you think should be the first step in this SN1 reaction? Is this a good leaving group or
Bad.
a bad leaving group? So what should we do first?
Add a proton.
Make it
From the acid and make it a better leaving group. Agreed? Everybody okay? So the base, this is an acid-base reaction. This is not a substitution step. But the bad leaving group becomes a good leaving group. See, that's the same in both. It didn't matter whether it's SN1 or SN2. We need a good leaving group. We good, everybody?
Mm-hmm.
Now we are ready for SN1 because we have a good leaving group. So what should be the next step? SN1 only. We are only thinking SN1 right now.
The OH2 gets taken off.
So what does it create?
A
carbocation.
carbocation plus water.
Do you agree, everybody? Everyone okay?
Yeah.
Cool. What's the next step? What happens to the carbocation?
It gets a chloride.
It's attacked by the nucleophile, in this case the chloride attacks the positive and gives us the, in this case, the product. Can we stop there? Can you tell me which of these three steps is the actual SN1?
Steps 2 and 3.
This is where the substitution is happening. That step is only to make a bad leaving group into a good leaving group. Is everyone okay?
Yep.
Can you tell me which of these three steps will be the rate determining step?
Step 2.
Absolutely. It's always the formation of the carbocation step that is the rate determining step wherever it comes. Are we all good? Okay, so the question I asked you in the lab yesterday, which was for something similar, this is not the major product. Can you tell me what will be the major product in this example and why? Okay, let me ask a question differently because I realize maybe you don't know part of what I just asked. Okay, fine. There is another product, major or not, we'll discuss that later. There is another organic product we should get in this reaction. Can you tell me what is that? Anybody? Nobody? Somebody?
Something that we don't see there, or something we
It's
see there, it's right there?
It's right here.
And you need another organic?
There's another organic product we should have here. Major or minor, we'll discuss that later. I want you to tell me what that would be. Were you saying something, Erin?
I'm gonna guess, we attach the CL on the other end.
There? Why there? Do you mean other
It's
end
similar,
as
like,
in here?
And it's not as congested as the other option.
But that's sp3 hybridized carbon with 3 hydrogens on it.
Not only that, it's identical. Or
Oh.
basically identical.
Oh, thank you. I totally didn't think about that. If Cl goes here, it'll be the same thing. Although if I drew this.
Right, well, okay.
Is that what you
okay,
mean?
yeah. Alright, point, I guess I was just thinking the other slot would be the other carbon, but I was just, yeah, alright.
What's the other carbon? Yes, you're right. The other slot is the other carbon. Which other carbon?
The other allylic carbon, or allylic, yeah.
So,
There's no leaving room there.
But,
Vinylic carbon?
I think it's gonna be some of its SN2 reaction.
oh, okay,
That's what I'm thinking.
yeah, I'm confused, never mind.
That's okay.
On the other side.
Okay, think about the carbocation, guys.
that's what.
Yeah, what?
No.
Go ahead. Think about the intermediate. Remember, this is a rate determining step. This has as an intermediate. What's the intermediate in the rate determining step?
The
That
carbon
everything
cation.
depends on. SN1 depends on that. Yes.
Carbocation.
Exactly.
Oh,
good
resonance, okay.
one.
How many of you were thinking resonance but didn't say it?
Not me.
I guess I was partially thinking
Somebody
that.
said, oh, this was a few years ago, in organic every end says resonance. I'm like, maybe not every, but definitely 3/4.
Yes,
It's a lyric, right?
right.
So
So you
can
can
it
do
do
resonance.
resonance?
Yep.
Can you tell me what's the resonance structure? Please. What's the resonance structure? Let's draw it, guys, paper to pen.
Good idea.
What's the resonance structure? If these electrons shift here because there's a positive charge, what does that give us? Agreed?
Yep.
Can the nucleus, is one bit, okay, wrong question. Do either of these exist?
No.
No.
What exists?
The resonance hybrid.
What does a hybrid look like? With dots. Is that it? What
Yeah.
else?
Partial charges.
Where?
Partial pluses.
It, yeah, oh yeah. Where it's
So where is the
Carbon super.
nucleophile going?
In between the two.
Is the there's no plus there.
It's going to either of them.
Let's use our critical thinking here.
It's gonna go on the carbon.
Can the nucleophile go here?
Yep.
Yep, it did. Can the nucleophile go here?
Yep.
Why not? So what's the other product? The other product is from the resonance structure. Absolutely. Everybody okay?
Yep.
Cool.
Oh no.
So let's talk about carbocations a little bit more, guys. We talked about this a tiny bit in the lab, but let's elaborate on this more. A carbocation,
That's interesting.
based on VESPA, what should be the shape at the carbon?
Trigonal
Louder.
planar hybridization is
Okay, if this should be
sp2.
trigonal planar, what should be the hybridization state of the carbon?
sp2.
So, how many hybrid orbitals does that carbon atom have if it's sp2?
Free sp2 hybridized orbitals.
And those orbitals are being used for sigma or pi.
Sigma
You
bonds.
guys agree? One sigma bond, another sigma bond, another sigma bond. What else does that carbon have?
A pi bond.
Which in this case, does it have any electrons?
No.
That's why it's positively charged, because this is empty. Unlike radical, in radical there was one electron in the p orbital, right?
Yep.
Neutral. In carbocation, this is empty. Everybody okay? Okay?
We still have it, but it's empty.
Yeah, of course, yeah, yeah. Everybody okay? Okay, cool. So, based on this, let's talk about relative order of stability of carbon ions. What kind of groups attached here will make this more stable? Groups that take electron density away, or groups that push electron density to the carbon?
That give electron density?
Isn't that right?
Yep.
Because you have positive charge. So if you have things that actually, we want some things that actually push electron density in that direction, so the plus becomes stable. Alkyl groups are weak electron donors. Please always remember this. R groups donate electron density, although very weakly, but they do donate electron density. Therefore, primary carbocation, would it be expected to be less or more stable than a secondary carbocation?
Less
A primary carbocation is something that has, okay, fine, 1R. Is this more stable or is this more stable?
Is it opposite, secondary?
Do you guys agree? The more R's, the more stable. Because R's are pushing electron density into the C+. So the plus becomes more stable.
Like,
Does that make sense? I'm hungry, you give me food, I'm happy.
like with the radicals.
Right, exactly like the radicals, for the exact same reason. Is that okay with everybody? So what about tertiary? Would you exactly. Even more stable, just like the radicals, even more stable than the secondary. Of course, if there's resonance, like allylic and benzylic, then they are even more stable. Because resonance is a much stronger effect than inductive effect can ever be. Resonance is a very strong phenomenon. Now, one thing I didn't put one here, maybe I should just to complete the picture, is methyl carbocation. That's even less. Do you guys agree?
Yep.
Now guys, please make a note, because this is different from radicals. In radicals, we made primary radicals and I was okay. However, carbocations never make primary or methyl carbocations. They are so unstable that they do not exist. Cannot. So if we are writing a mechanism, do not ever write a mechanism that invokes either a methyl carbocation or a primary carbocation, because they are very, very unstable.
Therefore,
Radicals you can, but carbocations you can't.
so we write primaries as an SN2.
Exactly. That's why primaries can never do SN1. Because their carbocations are extremely unstable. Yes?
But for like a lab, for example, when we're talking about the order of stability, can we include them, or would we still not?
Hopefully they didn't react. Again, I'd forget the list of compounds you have, but if it were methyl or primary, hopefully you didn't get SN1 at all, because they shouldn't.
All of mine react.
There was something really weird going on with your experiment from what you told me, which I have no explanation for. But now hopefully you know what to expect. Guys, are you okay? Everybody?
Yeah.
So now can you tell me which will be the major product?
The
1 or 2?
2
Why?
Secondary.
secondary carbocation.
So the major product, this is regioselectivity. In SN1 reaction, there is a matter of regioselectivity, especially if there's resonance involved. The major product comes from the more stable carbocation, just like the radical, where the major product came from the more stable radical. Similarly, the major product comes from carbocation. You guys with me? This is for SN1. Of course, in SN2, there's no such thing because there's no intermediate. Nucleophile goes exactly where the leaving group is supposed to be, so you don't have any choice there. Everybody okay? Let's talk about stereoselectivity. So, okay, let's take that major product. Can I erase the mechanism? Because you've written it already?
Yep.
Okay, cool. Let's look at the major product in this example. Just the major product. Does it have a stereo center?
Yep.
Everybody agrees?
Yeah.
I'm only thinking about the major product right now. Does it have a stereo center?
Yes.
So how many of those will I get?
2.
2. Which 2? Can you draw those 2 for me? Which 2?
RNS.
Agreed? Is there one major than the other? So let's, oh shit, sorry, didn't say that.
We're getting close.
At least I'm not as bad as using the F word, but I'm learning. Shoot, I shouldn't have deleted, erased that. When I came here as a grad student, I came in '93. And I came as a grad student, I was a TA. I was assigned to be a teaching assistant. And I think first or the second class I was having with students, I was using the S word pretty frequently. Till after class, somebody came and told me, a student came and told me, that's not polite to say. And since then, I have been very, very careful. So I didn't say that. If you heard me say that, you're lying. Coming back. I shouldn't have erased it because I needed that to explain. So the carbocation is sp2 hybridized, right?
Yep.
It has an unhybridized p orbital, which is empty. Isn't that right?
Yep.
What's the shape of the sp2 orbitals?
Trigonal
Good.
plane.
Thank you. So, so the question is, when the nucleophile comes in, whatever it is, does it prefer coming from this side or does it prefer coming from this side?
Doesn't matter.
It
Is
doesn't.
one approach better than the other?
I think either approach is equal.
Do you all agree? Again, my Dr. Spock fingers, if you have trigonal planar with the p orbital, does the nucleophile come from here or does it come from here?
Any direction.
Both. They're both equally accessible because none of these are blocking the approach of the nucleophile because they are planar. So either it comes from here or it comes from here, equally likely. Isn't that right? So, which should be major or minor?
They're same.
Equal, exactly.
They're the same.
You will get equal quantities. What do we call that when you have equal quantities of opposite enantiomers?
A racemic
You
mixture.
will get a racemic mixture. Exactly. So what is the stereoselectivity of SN1? Stereoselectivity.
Do you call it racemic or?
Racemization, exactly. You will get a racemic mixture, meaning that even if there were a stereo center to start with, there will be no stereo center in the product because it will get racemic. Excuse me, you will, let me say that again. I did not say that correctly. Let me write it and I'll say it. So let's say we take this example. Any guesses, product? Please?
The O on the CH3O replaces the Roman.
So just the O?
Well, like that's the part that connects.
So just the O?
No, but that's the only part that connects.
Okay, so
The
what is?
The CH3
Oh,
are cell
perfect,
type.
perfect. And byproduct?
HBr.
Okay, let's write a mechanism to understand. Shoot, that's not a stereo center. Okay, let's make it a stereo center. can I make this, can you tell me if this is R or S, the reactant?
Um,
Is the reactant R or S?
R.
Is it R?
no.
R.
Oh,
Wait.
how can you? You should tell me, Sumita, fix your drawing. You should say that. Go ahead, say that.
Sumita, fix your
Picture
drawing.
drawing.
What the heck?
Now I fixed it. Is it R or S? Priority 1,
R,
2, 3,
3, 4, it's
4 is
R,
back. So 1, 2, 3, is that R or S?
R.
Okay, cool. Of course, you can name it. You should know how to name that compound because we've learned how to name alkyl halides, but that's what, okay. So what about the product? So how many organic products would we get?
2.
2. What would they be? One would be,
OH on a wedge.
there's no, not OH. The
Oh.
nucleophile is OCH3.
Oh,
because
CH3,
will be bound.
okay.
And we'll write a mechanism. So one is this, do you agree?
Yep.
Which is the same retained, stereo center is retained. And the other will be what?
The OCH3 on a dashed line.
And on the wedge is what?
The
Just
methyl.
the CH. Inverted. You'll get 2 enantiomers. So even though we started with 1 enantiomer of the reactant, we ended up with a racemic mixture of the product. Everybody agrees? Sees that? Let's write a mechanism quickly. What's the first step? Yeah? Leaving group leaves, right?
Yep.
And makes a what?
A carbocation.
Because it's already a good leaving group, so we don't have to do anything. So it leaves, it makes a carbocation. Now, is the carbocation tetrahedral or trigonal planar or linear or what?
Trigonal planar.
So make sure you draw it that way. It's trigonal planar. Agreed? It's not sp3 anymore, it's sp2. What happens next? The nucleophile, which in this case is methanol, attacks. Isn't that right?
Yep.
Does it come from the front or does it come from the back? Or both? Does the nucleophile come from here or does it come from the back or both?
I guess it depends on which stereo. Well, because one of the methyls going to be either pushing forward or pushing back.
That carbon is sp2. The carbocation is sp2. Right? That's sp2. This was sp3, I get it, but this is sp2. If this is sp2, it's trigonal planar, which means there is this unhybridized p orbital that's perpendicular to the plane of the trigonal plane. So where does the nucleophile come from? Does it come from the top or the bottom?
The
Or
bottom.
both? Both.
Both top
When
and
you have a
bottom.
carbocation, stereochemistry is lost. Because it's trigonal planar, then the next step can happen from either side with equal ease because nothing is really blocking it anymore. So, the point is, this is the step where the nucleophile can either come from the front or come from the back, or rather I should say it will come from the front and come equally likely to come from the back. So this is where we end up with 2 different products. As soon as the carbocation is created, we lost stereochemical control. We don't have control anymore. Because carbocation is trigonal planar, which means the next step can happen from both sides equally likely. In equal amounts, rather, I should say. We good, everybody? What should happen next? That's not the product yet. So what needs to happen next?
Acid base,
Acid base, who's gonna act as the base?
the CH3OH.
We have an option of course, Br minus was created here. So the question is it Br minus or is it methanol, which is a better base? Methanol, as you've already noticed, that Br minus, X minus, they're not good bases. X minus is Cl minus, Br minus, not very good bases. So, exactly. This comes in as a base this time to take that proton, give us the product. Will you be able to write that step for the second product, everybody?
Yep.
It's the same, just with a different stereochemistry. Everybody okay? The point I'm trying to make here, which is a very important point, do you remember stereoselectivity for SN2? What happens stereochemically for SN2?
It switches.
It switches because a nucleophile must come from the opposite side of the leaving group, so there's inversion. Let's use the word inversion of stereochemistry. Isn't that right?
Yep.
Wedge becomes a dash and vice versa. Here, it becomes racemic because as soon as carbocation is produced, we don't have any control on stereochemistry anymore. We will get both options equally likely. Of course, one is favored, but we are not getting into that. Theoretically, on paper, both are equal amounts. Racemization, it's called. Yes?
So you're saying one is favored, I might say one thought later, but is that?
I'm not going to go into that. I don't think the book does too. It has to do with solvent. It actually has to do with solvent. It has to do with, practically speaking, if you're thinking about, practically speaking, you asked. When this is breaking, for even a short amount of time, probably this hasn't gone too far and it's blocking one place. So the nucleophile can come from the other side only, but for a small amount of time. So that gives it an edge, a little bit of an edge. We're not going to talk about it. For us, SN1 produces a racemic mixture and we're done. Are we okay, everybody? Yes?
Yep.
Questions so far? Okay, let's look at the factors that affect rate of SN1 reaction. Just like for SN2 reactions, we will go over the 4 factors that affect how fast or slow an SN1 reaction can go. So can somebody remind me what's the first factor we look at? Substrate, exactly. Substrates. So, can someone tell me what let's see. What kind of substrate will go through SN1 fast? Louder?
3.
What do you mean by 3? Tertiary.
Tertiary,
Let's use the right terms, primary, secondary, tertiary.
tertiary carbocation.
Because it's about the stability of the carbocation. The idea here is that the more stable carbocation, faster is the SN1. Because it's the formation of carbocation, that's the rate determining step. So absolutely, typically speaking, tertiaries, fast, secondaries, okay, primaries, never. They don't do SN1 because they can't make a stable carbocation. Of course, allylic, benzylic, yeah, absolutely, they can do because the carbocation is stable. So absolutely, yes.
You said about more stable is the rate determining step.
Carbocation formation is the rate determining step, right? When we write the mechanism, it's this step that's the rate determining step. The step where the carbocation is made. So the more stable that guy is, the faster is the reaction, basically. Okay? Everybody okay? Any questions about that? Okay, what's the next factor we look at?
Nucleophile.
So does the nucleophile come into the picture for SN1? No.
No.
Please remember that when we wrote the rate equation, when we said rate is equal to K times concentration of substrate, is nucleophile part of it? So
No.
does it matter? Will nucleophile ever affect the rate of SN1 reaction?
No.
No. That is the reason why we use weak nucleophile for SN1. For SN1, it is always a good idea to use a weak nucleophile because it really doesn't matter. Everybody okay? What's the third factor? Leaving group. So do you think we need a good leaving group for SN1 to happen? Again, look at the rate determining step. What's happening in the rate determining step? This is your rate determining step, right?
Yep.
What's happening here? You're making a carbocation. Why? How?
The leaving group is
Leaving
leaving.
group left. So do you think we need a good leaving group for that step to happen?
Yes.
Yes.
No, absolutely.
Definitely.
In order to make, and the same criteria of what's a good leaving group, that's the same definition as SN2. But if you have a good leaving group, that's when it can leave and make a carbocation. Does everybody see that? So yes, the better leaving group, SN1 would be. Everybody okay? What was the fourth factor? Solvent. So, SN1 reactions are better by using a polar protic solvent. What is a protic solvent?
A solvent that can
Contains
give an
protons.
electron.
Electron.
No, proton.
Proton. Such as? What solvents have you seen that can actually give a proton? Louder?
Water.
Water. What else? What is like water?
Alcohol.
Alcohols. Typically that's what you see. And that's why they are solvolysis reactions, because A, they are weak nucleophiles, protic solvents, so why not just have them be a nucleophile and do SN1?
Carboxylic acid.
Although not for solvent, not very typical to use carboxylic acids as solvents, but those are the common ones. So we need polar protic solvents to make SN1 go faster. Everybody okay? Everyone? Yes, question. So do we all understand this? Stability of carbocation. Any questions? Do we understand regioselectivity of SN1? More stable carbocation, major product. Do we understand the stereoselectivity, or rather lack of stereoselectivity? It's racemization, because carbocation is planar. Any questions so far? Okay, let's summarize SN1 and SN2. Let's look at both of them together and see if given a choice, can you predict whether a substrate will go through. Oh shoot, no, not yet, sorry, not yet. Can I take a step back? Yes. There's very important thing about SN1 that how could I even forget? Okay. Okay. Product.
OH replaces the BR.
Sorry, could you say that again?
OH replaces the BR.
Okay, so OH replaces the BR is the answer I got. How many of you agree? Assuming SN1, of course. And yes, it will be SN1 because that's a weak nucleophile. So it will be SN1. But do you guys agree?
Yeah.
What if I were to tell you it's not the major product? It's not the major product. Is there resonance here for us to say?
No.
No. Then what the heck is she talking about?
Exactly.
Exactly. The major product is, in this case,
What?
yes. So let's pause. Let's pause. If you just focus on the major, we all understand this, right? We can write a mechanism for this blue one. Total. Let's focus on the red one, which is actually the major product in this example. Let's focus on that. First of all, is it substitution, elimination, or addition reaction? No. No. It is substitution.
I think,
Br got replaced by OH.
substitution,
But-
rearrangement.
With rearrangement.
Oh,
There's rearrangement going on.
I swear that was.
Here is the trickiest thing about carbocations, which you have to learn to recognize through practice. Only for carbocation, only carbocations can do this. Carbocations can rearrange any mechanism, and we will see this several times throughout the quarter. If the mechanism has a carbocation, you got to be on a lookout for a possible rearrangement. Of course, I'll tell you what to look out for in just a minute, but you must always remember that they can rearrange. There are two kinds of rearrangements that I need you to learn to recognize, and we look at those examples. You should learn how to recognize either what is called a methyl shift or a hydride shift. And the purpose of rearrangement of a carbocation is to make a more stable carbocation, always. That's the only driving force for the rearrangement to happen, is for one carbocation to become a more stable carbocation. You guys with me? So let's look at this example. If you were writing a mechanism for this one, what would the first step be?
For the blue or for the red?
The first step will be the same for both of them because it's SN1. What would the first step be?
Kick out the BR.
The BR gets kicked out, creates a what? A carbocation. Do you guys agree?
Yep.
Of course, if this reacted with water, you would get the blue product. Isn't that right?
Yep.
And of course, that gives us the blue product. Everything seems to be okay. But the carbocation actually can rearrange, because from one of the next carbons, only the next one, you don't have to look farther than that, adjacent carbons only, either an H can shift or a methyl can shift to create a more stable carbocation. Let me show you two options. Either, are there hydrogens on that carbon, right?
Yes.
So either one of these hydrogens with the electrons, hydride meaning with the electrons, moves here. Please notice the curve of the curved arrow. What does that create? Anybody? By the way, originally how many hydrogens did that have?
2.
Careful. If
One.
there were two, why would there
One.
be a positive charge? How many hydrogens did that have?
One.
So when Br left, how many hydrogens is it left with?
1.
1. Now how many does it have if one of the H's moved over
2.
here? 2. Do you agree? How many hydrogens left on that carbon? 2. So where's the positive charge?
On the end.
Agreed? That's a hydride shift. Do you all see that? But there can also be a methyl shift. Again, from one of the adjacent ones. Can one of these methyls move?
Yes.
Again, with the electrons. So let's see what that does. What does that create? Now, what's on this carbon?
A hydrogen.
Okay, what else?
A
A methyl moved.
methyl moved.
Isn't that, and yes, there's a hydrogen there too. Agreed?
Yep.
What's on that carbon?
A methyl.
There were 3 methyls, one moved, how many left?
2.
Where's the positive charge? Okay, fine, I'll draw the hydrogen if it has
On
single
the
state.
two, on the two,
Where's the positive charge? Who lost electrons?
on the isopropyl group.
Do you guys agree? Everybody okay? That's a methyl shift. So two kinds of rearrangements that I need you to recognize anytime there's carbocation mechanism. One is a hydride shift that a hydrogen with the electrons from next door moves, or a methyl shift. But do we understand the two shifts? Now I want to ask you, which of these two, what kind of carbocation is this? Primary, secondary, tertiary?
Primary,
Oh, by the way, what kind of carbocation was the original one? Primary, secondary, tertiary?
secondary,
Okay, so it became from secondary to primary. Is that becoming more stable or less stable?
less stable.
Doesn't happen. It's all going towards higher stability. That's the goal. If a more stable is becoming less stable, why? No need. Agreed? What about this guy? What kind of carbocation is this? Primary, secondary, tertiary?
Tertiary,
Is that becoming more stable from before or less stable?
more stable.
Absolutely. Carbocation rearrangement goes towards more higher stability. So I'm out of time. So here's what I need you to do. Again, I will not be going over this anymore because I'll do more examples on Monday of rearrangement because we only just started rearrangement. But please complete this mechanism. Okay? What about this carbocation? What would be the product? One last thing before you guys go. Comparing this carbocation, the original one that gave us that product, comparing the rearranged carbocation that's going to give us the other product, which product do you expect to be the major product? The blue or the red?
The red.
The major product comes from the more stable carbocation, period. Whichever carbocation has a higher stability will give us the major product. So since this is more stable, its product is the major product. You guys with me?
Yep.
Please complete that so you get in the habit of it. Please keep working through that handout I gave you guys. I think the key is on Canvas. We will do some more examples of SN1 with carbocation rearrangements on Monday after the quiz. Is it a quiz? No, there's no quiz on Monday, right? Because there's an exam on Tuesday, am I right?
Yes.
Maybe not the rearrangement part, because that would be too evil of me to do so. But can SN1 be on the exam? Yes.
Yes.
But not with the rearrangement part. So no quiz. So okay, that we'll do. Then we'll do the comparison between SN1 and SN2, and then we need to start elimination because it's all one big thing. So that's the point. Plan for Monday.
So there's class on Monday?
Yeah. Why?
Why?
No, am I missing something? No, no. I'm not. They are making fun of you. I'm not making fun of you. Is there something on Monday?
No, I was just curious if like Monday's lecture got canceled right before it goes.
Oh, never.
I
No.
think one of my other classes did that.
No.
Yeah, biology.
How does he get enough time to then cover the material?
How do we cover the material if there's no
No,
class?
I'm sorry, we can't do that.
Well, it was a lab.
Okay, I'll see you guys
lab, right?
upstairs.
My
Yep.
senior assassin.
With the guy, the neuroscience guy, for our group. He did big balls.
I
You said hell yeah. But he's from Germany.
close enough, right?
Yo, that's so wild. He doesn't like it, but we're gonna do
I don't care. I was kind of half joking about the bombs thing.